It's an honor for me to be here together with such brilliant people that I admire so much. I humbly hope that I can contribute with my little grain of sand to this wonderful event. During the majority of my career, I barely managed to survive. Things drastically changed when I discovered, nearly by accident, TDD 6 years ago, as Dave has pointed out, when I found that Reusable book from one of our speakers, the Master James Greening. If I will have to give any simple recommendation and end this presentation just right now, will be to go for it. So let's begin. What's an embedded system? It's a computer system with a dedicated function inside a larger and customized electronic system. It's composed of one or several microcontrollers, which are the brain of the system, as well as peripherals divided in sensors which sense the environment and actuators which respond to the environment in an autonomous manner or upon external commands. So an embedded system is made of hardware, firmware, and hopefully some piece of software. But what is really hardware? We all will agree that the yellow shaded area is hardware. But what about the microcontroller itself? It's a piece of silicon, isn't it? Well, from the point of view of embedded code, the special function registers are hardware, as long as each microcontroller unit has its own implementation. Special function registers are a simple way of having the hardware mapped into a set of memory addresses, in which each single bit has a special meaning. They are the gateway interface to the real world, the world that our embedded system senses and tries to actuate accordingly. And that point is extremely important for us, as long as from the point of view of the embedded code, absolutely nothing happens in the real world if it doesn't change a special function register. So we have now clearly delimited where the embedded code ends and where the hardware begins. But that embedded code, is it firmware or is it software? I love the following definition from James Greening in a Clean Architecture book from Robert Cecil Martin. He states that the software is this thing that can have a long, useful life, but firmware will become obsolete as hardware evolves. He also states that the firmware is firmware because of what it depends on and how hard it is to change those dependencies. When some dependencies are hard to change, we will indicate it by using this icon in this presentation. Another piece of gold from James is when he explained that non-embedded developers are also write firmware whenever they spread libraries or platform dependencies throughout their business logic code. This is a great advice. If you are an embedded developer, be aware that the special function registers are not the only thing that you can end up being firmly tied to. Your operative system, real-time, or vendor libraries, for example, are also excellent candidates to end firmly depending on. Let's move now to the three well-known and desirable steps of software development that we know as make it work, make it right, and make it fast. During the make it work phase, we are focused in understanding how to solve the problem, not about engineering the code right. In the make it right phase, we are supposed to be engineering and crafting the code right to make it easy to understand, maintain, and evolve. These two differentiated steps should exist because barely no human being, and therefore no software developer, is able to do both things properly at once. And the last step is make it fast. That means that fulfill the system requirements, if any. Let me now introduce or opening now a section in this talk that I named fallacies and mantras. And here comes the very first and the biggest lie ever. And it states that the fact that you are not going to obtain the right solution at your first iteration. It's impossible both in the embedded and non-embedded world. But if there's something that is a major difference between embedded and non-embedded world, in my opinion, is that making a simple thing to work is orders of magnitude harder in the embedded world. And this is because we have to manage lots of little low-level details at once in order to accomplish a simple task. Additionally, there are other problems because the underlying running hardware platform is scarce, non-existent, or even faulty. In my opinion, starting from our academic studies, continued by naively following most of the examples and application notes coming from the manufacturers themselves, and finally perpetuated by the lack of really senior embedded developers out there, some of us, like me, have faced the situation illustrated in this slide, which is known as the main God. This is an example of how it looks like in code. It can clearly see how the single main module is in charge of everything, including interacting with the hardware. That has a direct consequence. The code is firmly tied to the specific running microcontroller unit, and additionally to the target cross-compiler. The reason for that, the last sentence, is because the cross-compiler offers some kind of aids in order to safely interact with the special function registers. So why are not we going to naively use them, right? Moreover, the code knows exactly which integrated circuits are being used in the current solution, that is, the current hardware or printed circuit board. So it's firmly tied to use these components in order to perform its higher level duties. And the hard-to-change dependencies don't end here. The code is also fully aware about how the microcontroller unit is connected to the integrated circuits in the current PCB layout. For these reasons, we can safely affirm that this code is firmware. It's firmly tied both to the running microcontroller unit and to the underlying hardware platform. If we attend to design principles, like solid, for example, we can say that it violates all of them. But I am quite sure, however, that many of you will have been lucky enough not to have had to deal with the main God like I had to do, because you have used layers. Specifically, what we commonly know as the drivers IC layer. In this layer, we put all the modules aimed to command specific IC peripherals accordingly to their datasheets. In order to do that, the EC driver modules use the special function registers to drive or communicate with the chip, which again makes these drivers strongly dependent on the running microcontroller unit. That means that it's not possible to execute them by another microcontroller, or in other words, they are not portable. This is a clear violation of dependency inversion principle because a higher level entity, like the driver in this case, depends on low level details like are the running microcontroller unit. And what about the code that uses the drivers layer, that is the application layer? Well, it knows which integrated circuits are currently used, as long as it's directly calling its public APIs. So that supposes a clear violation of the dependency inversion principle. The application is supposed to be a higher level entity, but it depends on low level details. And also a clear violation of the open-close principle, because we are not open to substitute, for example, an IC for another one that extends functionalities without having to change the application code itself. As I resume, we have improved a little bit the cohesivity of our solution if we compare with the main God, but the underlying problems are still there. Some of the problems of the main God are common to embedded and non-embedded world. Like, for example, we have no long-life software in charge of capturing domain or business logic. Nothing is modular or reusable. It's impossible to test any part in isolation. We are forced to perform manual testing and debugging, which leads to an expensive and hardly repeatable process. Additionally, due to being embedded, the main goal of this code is only to be able to be compiled by the selected cross-compiler. It's only executable under a specific microcontroller unit, and it runs only under a specific hardware platform or PCB assembly. As a result, expensive and scarce powering, input generation, and output measurement equipment is needed. All these problems materialized in a huge bottleneck for our development process known as the hardware bottleneck. And this is how the hardware bottleneck usually materializes in an embedded software developer workplace. And hardware bottleneck presents lots of issues. When we are forced to debug the code directly on the hardware, we are exposed not only to the bugs coming from the software or the code, but also to the errors coming from the hardware itself. If we try new code directly on the hardware and it doesn't work as expected, where is the problem located? Is it hardware? Is it firmware? Is it both? This situation commonly leads to a lack of trust, preventing us from behaving like a real embedded team. The aforementioned problems tend to lead to the sensation of apotheosis when we finally manage to bring up the system. We tell to ourselves, yeah, it was complicated, but we finally made it work, without realizing that the vast majority of this complication was not essential, was accidental. Which are the reasons that have led us to this discouraging situation? In my opinion, in the embedded world, and also non-embedded, but we have more problems in the embedded world, and I call it traps. Let's go to the first one. This trap is typical for the embedded world. I call it the vendor's trap. Basically, what this says is that the vendor IDEs, frameworks, utilities, tool chains, libraries must be low-level details, properly hidden from your application. Or in other words, the vendor is not your partner. At the end, the running processor should be a low-level detail. Another trap that is more well spread in the embedded world is the compliance mindset trap. First, let me define the quality in 4 quadrants. One axis represents what is visible to the client. The other axis represents the kind of value, positive or negative, both to the client and to the organization. On the left side, we have 2 quadrants visible to the client, which conform what is known as external quality. While providing new functionality and features has a positive value, delivering products with defects or bugs has a negative impact. Most of us became interested in testing to prevent or mitigate the number of bugs delivered to our clients. In the better world, we have some epic and historical failures in our mind. Like, for example, the 42nd flight of the Ariane 5 originated due to an overflow when converting a 64-bit floating point number to a 16-bit signal integer. Or the TRAC-25 linear accelerator, which killed at least 6 patients after receiving 100 times overdoses due to race conditions in its deficient software. Or the 89 deaths originated by the unintended acceleration of some Toyota models, as James has already pointed out, due to an overflow problem on the real-time operating system stack. To prevent these situations, safety quality standards are considered the crown jewel of preventing bugs inside the embedded world. Most of their recommendations are followed consciously or unconsciously by the vast majority of embedded developers. For 6.15.08 standard, dynamic testing is considered the primary functional validation technique. For these reasons, and accordingly to each safety integrity level, it points a clear focus on code coverage. 100% code coverage is highly recommended, which means somehow mandatory, for those systems with the highest safety integrity levels. Let me make a little introduction to a powerful technique that is still not required, as far as I know, in any safety standard, and it's called mutation testing. It's an automated fault injection, a technique aimed to find counterexamples to this conjecture. Our test suite is comprehensive because it has 100% code coverage. So it is aimed to automatically measure the quality of our test, or also known as our self-checking specifications. Here you can see a code example from the kata we developed during my Unembedding embedded systems course, a temperature controller. You can see that it reads the temperature on line 19, and it compares to a configured threshold. Depending on the situation, sends a temperature control action to set an actuator. As you can see on line 21 and 22, lines 21 and 22 are not exercised by the test suite, so they are not covered. The 20 mutants of these 2 lines pass the tests, which is known as they are alive. What it means is that our test suite is not comprehensive or semantic stable, as long as these two lines could be completely removed and the test suites will not notice it at all. So even if a 90% code coverage could look like a great number, it isn't. And now I am starting another section of in the presentation that is, I call it fallacies and mantras. One of the fallacies that I have from time to time is that code coverage is an useless metric. And sometimes it adopts other forms, like, for example, we have 100% code coverage and we are still having defects, so we can give up on that metric. And that's wrong. We can strongly affirm that any part of the code that has not been executed by the test suite is for sure out of our control. Code coverage metrics helps us to locate and identify these zones. The only valid target for this metric, even being difficult to reach, is 100%. Obviously, if we follow TDD, 100% code coverage is taken for granted. And another way to say it is that 100% code coverage is nothing less than a precondition to have a comprehensive suite of tests. Having this in mind, why does a functional safety standard allow any value below 100%, at least for the lower safety integrity level systems? Not only that, but also why does it open the possibility to accept code coverage below 100% if an appropriate explanation is given, even for the highest level safety critical systems? The only reason I can imagine is to somehow be permissive to accommodate certain test later approaches inabilities. Let's see another example. Now we have 100% code coverage, but there are still 3 mutants alive. The mutants on line 20 and 24 are symmetric. We can go to the alive mutant in line 20. What is this mutant whispering to us? As you can see, what it has done, it has changed this greater for the greater or equal, and our test suite is passing. So what it's really saying is we have not specified which is the expected behavior of our code for the equality. If we add this corner case, in that case you can see that we have 2 tests, one for each of the symmetric cases, we kill the mutants. What it means that we have improved the semantic stability of our tests. So let's see now. Let's take a look to an empirical study of the application of mutation testing in a safety critical system coming from the industry. It's applied to 60,000 lines of code, of C code, which has obviously 100% full code coverage. They pick when the mutation testing was run, it gave to them 27,000 survivor mutants, more than 27,000, and they pick a sample of 200 live mutants, and they analyzed with the engineering team. They found that inside these 200 mutants, there were two faults on the production code. If we extrapolate these numbers, considering a uniform distribution of defects, we will end up with the possibility of having 271 faults, defects in the code awaiting to be executed. Another of the fallacies that related with the code coverage that I heard is that code coverage is a harmful metric. And the underlying reason behind this affirmation is that many developers try to hit 100% code coverage because they were somehow mandated to do it without knowing the real implications. Some of them end up cheating the code to artificially increase the code coverage. That leads me to another section on this presentation that I call it takeaways. And the first takeaways is that this is not a metrics fault. Cheating the metrics is a sign of bigger cultural and professional problem. If you add mutation testing to your workflow, the cheaters will be unmasked. And what about agile and extreme programming inside the safety critical system world? Well, this is in the ISO 26262, which is an adaptation of the AEC 61508 for the automotive industry. Even when the reference software development process is the V model, they are finally opening to accept approaches and methods coming from the agile world. Specifically, as we can see in the example one, it's saying that the trace-driven development can be used to improve quality and testability of requirements. And that's a great news. That are great news, because it will unconsciously reach to a larger number of embedded developers out there, more or less like it arrived to me. Well, most of you will be now thinking, okay, but I'm not working in a safety-related environment. Okay. As Diane Bauman, that in her book, The Challenger Loan Decision, she says that if non-accidents, that's the cases that do not reach the general public, were investigated, the public will discover that the messy interior of engineering practice is nothing more or less than normal technology. So that is how we proceed in our jobs, more or less. We will be returning to this later. Another of the common, this is a common trap, is not only from embedded, is the deviated focus. As I said, most of us became interested in testing or even TDD to prevent the number of bugs we were producing. But bugs, and also our inability to deliver new functionality in a sustainable pace, are only the visible effects of another most important aspect that we will see in a moment. Let's take a closer look into the TDD red-green refactor steps. As I said, making a simple thing work is orders of magnitude harder in the embedded world. If we use TDD, we will be trying to bring up new functionality in this phase, in the make it work phase. That is when we go from red to the green. And we will try to do it as fast, as simple as possible. And here, everything is permitted. All the things are allowed. The thing is to touch the green bar as soon as possible. In fact, this is something that is nothing new to us. It's what we have done so far during these years. But it's on the making it right phase, when we enter into the refactor phase of the TDD, when we are supposed to engineering and craft the code right. That means that this is the phase where we must engineer our code right. Here's where we apply software engineering practices like simple design, solid design principle, design patterns, and it's here where we take a closer look to our dependencies and try to properly manage them. TDD, do it correctly, it's aimed to improve our internal quality. The two right quadrants, which conform what is called internal quality, even invisible to the client, are more important, because when we have a well-engineered code, the number of defects are much more smaller, and so the bugs finally delivered to our customers. As another takeaway, we will say that our internal development and quality standards must be there in order to raise our internal quality high enough to preserve our organization, enabling us to deliver value to our customers in a sustained pace. If we do it properly, fulfilling any other external quality-related standard will be taken by granted. But okay, what about making it fast? We are embedded developers, and we usually have tight timing requirements, even if we are not developing real-time systems. Well, I delay presenting this development phase consciously, as long as it's related with the very last of the traps common in the embedded world. And I call it the global performance pre-optimization trap. As Ron Jeffries says in the Refactoring's book of Martin Fowler, even if you know exactly what is going on in your system, measure performance, don't speculate, because you will learn that 9 times of 10 won't be that you were right. So it means that 9 times of 10, you will make useless optimizations. So the first question should be, how fast? If we don't have a clear specification, now is the moment to clarify it. Once we have an adjective number, then is when we finally have the timing specification and not before. Once we have it, what we need to do is to translate this timing requirement into a self-checking specification, like the other specs. Your tests, for example, can use the microcontroller unit timers for this purpose. And you will, as another requirement, we will fulfill this requirement as fast as possible, all right? We don't have to engineer anything here. And once we are fulfilling this requirement is when let's make the code clean. Let's manage dependencies and do it while we are fulfilling the timer requirement. So another takeaway comes from Martin Fowler in his book. The secret of fast software is to write tunable software first and then tune it for sufficient speed. The last of the traps, that it's a common trap, and maybe is the most important one, is the knowledge and skills trap. No human being can escape to the Dunning-Kruger effect. The natural tendency is to think that we know more than we really know, at least until we become really seniors, which does not have necessarily a direct correspondence with years of experience, at least, as I said. High humidity threshold prevents us from continuing learning and continuing improvement. So we better should follow one of the most valuable advices from one of our beloved masters, Dijkstra. Be a humble programmer. So we need to move the quality boundary forward. And moving from making it work and the survival mode into a making it right, so behaving as engineers. So we need a new approach that is outside the usual embedded limits. As James Greening explains in his wonderful book, what we need is an embedded dual target TDD workflow. What we are going to do in the stage one, we are going to write a test, make it, but we are going to do the red-green refactor cycle in a host-based flow. That means on the machine where we are developing. We will generate the self-checking specifications. We will fulfill the specification as fast as we can. And once we are done, we are in that stage, we will improve our code iteratively every minute, with a cadence of every minute. For sure, the end machine is different from the host, so we need to run all the specifications and also our product in the target microcontroller or a target device. This is what we do. That's what we do in the stage 2 and stage 3. We will cross-compile our solution and we will execute the same tests in the evaluation hardware. Or if we found that it has lengthy loads, delay in the feedback, we could use a microcontroller simulator coming from the vendor. And here is where the vendor should provide the correct tools. So a microcontroller should be one of the things that we will need to have from a vendor when we select them. With a cadence of 5 minutes, maybe, or if we can do it with less time, the better. The fact is that when we run in the target environment, in the target-based flow, the feedback loop is going to be wider. So the main benefits of the embedded TDD is that it will remove the fear, because we will be incrementally developing our solution that is going to be comprehensively tested at least on 2 different platforms by default. The fast feedback loop will encourage us to try new approaches that were very far beyond before that. We will learn fast. That way, maybe we can fail fast, but the objective is to learn fast. Without limits, because we will have new tools finally available, like static analyzers, rule checkers, comprehensive functional and not functional testing, mutation testing. And when I say finally, I mean that they are going to be able to be applied to 99% of our code base. Only the 1% corresponding to the firmware thin layer being able to be processed by some of the tools. This tool set is going to be run automatically by the continuous integration and continuous testing server anytime a code change is sent to our source control server. This is an example of a pipeline that we see in my course, where we run several stages in the host, like static analysis, dynamic analysis, And we extract some metrics like code coverage, mutants coverage, and psychomatic complexity. The same kind of dynamic analysis is done in the target if everything was fine in the host, because, as I said, it took a little bit more time. We also extract some metrics, and one of the most important is the warnings from the cross-compiler. These warnings that we usually forget, and we have to go to a clean build. This is an example of the information that can be seen for each build. That allow us to give up or put us in a situation of an increased competitiveness, because we will have fewer defects, our developmental lead time will be reduced, we will have better market adaptability through portable solutions, and our code is going to be able to be done by anybody, anywhere, at any moment, and at a sustainable pace. That means, at the end of the road, improving our talent and acquisition and retention. And there will be no more excuses to develop complete embedded portable solutions made of reusable modules while using a common and shared language between development and business. That is, we will finally able to express ourselves in the terms of the domain. Well, if you remember, we led the solution or the code in that stage, but we are going to trying to make it right. So we will move towards reusable drivers. What we need is to put in place an abstraction layer. It's called processor abstraction layer. The PAL is aimed to hide the low-level details that each specific microcontroller internally performs in order to execute one of its possible tasks. For example, one of the modules conforming the PAL will be in charge of reading an analog channel, and as we will see later on. For sure, for each microcontroller unit, we will have to implement the PAL that we want to use. And this PAL is this layer, the PAL implementation, is the only part of the code that is going to be allowed to know and interact with the special function register of the microcontroller, which is the microcontroller hardware gateway. For sure, that means that it's tightly coupled to the microcontroller unit, but it's duty. And also to the cross-compiler, no problems. It's exactly what we want. This is why we call this thin layer the firmware or microcontroller firmware layer. In order to develop the reusable IC drivers, we could use test dowels, which will implement the PAL at our convenience. We don't need to run until the hardware. Of course, once the spec is established, we will exercise the drivers through the public API. The IC driver test suite goals is to capture our integrated circuit datasheet interpretation, allowing us to implement the EC driver accordingly to it without introducing errors, while removing the hardware bottleneck related uncertainties and delays. And what about doing TDD in firmware? Well, when we are working on a specific MCU PAL implementation, we cannot use any test dowel. What we need is to assure that we are interacting with the special function registers correctly, which means assuring that the sequence of reading and writing steps are correctly done and in the proper order and with the proper values. In order to do this, we could make use of the decorator pattern, for example, if we were in C++. But if we are in C, the only thing that we can do is to have StepByHooks in the code production itself that will be compiled only during testing. We don't have any other option. This is a production code example belonging to the PAL module in charge of reading analog variables. If I manage to communicate its intent, even if you are not an embedded developer, you could understand what it does. It's a statically linked template pattern which executes every of the steps needed to get analog measurement from an analog channel, delegating to each of the microcontroller implementation steps its details. The goals of the microcontroller PAL test suite is to capture our microcontroller unit datasheet interpretation, which allows us to implement its PAL according to the datasheet without introducing errors, making possible to use this microcontroller in our solution while removing the hardware bottleneck related uncertainties and delays. And what about towards embedded business software? What about the application? We let it violating dependency and open close because it was calling directly the easy driver layer. For sure, what we need is to create the proper abstractions related with those entities that only makes sense from the point of view of the system application, which I call system components. Each hardware implementation will implement these abstractions in order to be used by the application. For example, imagine that we have a temp sensor, right? Like a system of a component of the system is a temp sensor. If we have a temp sensor that is made of by the STH11 IC circuit, we will have a module that it will implement that. And it will use, obviously, the EC drivers, the driver of the STH11. That means that this layer, it's tightly coupled to the PCB components, but it's a purpose, no problems. How do we make our application independent of the components of the hardware or the PCB itself? Another pattern to the rescue, factory. We will use a factory that it will read from a configuration file which components are going to be used, and it will create them. Well, so far we have been now we have been talking a lot about the hardware, but let's go for business application development. What we will do is we will have system asserts. So we will test we will verify the behavior of our system with an abstraction of the system, what the system must done independently of which components or drivers are being used. It will implement, depending on the system, on its components or drivers, which are these assertions. And it will use the test double to check them. For sure, what we will need also is to, in the arrange phase, we will need to have somehow the main instrumented in order to stop it, because if not, we will be running forever. We don't want that. In the same applies to the arranges. We will have a system abstract arranges that each implementation will each component's implementation or hardware implementation will implement, and it will instantiate the test doubles. Once done, the application test suite will execute the main directly, and we will be listening or capturing what is going to happen at the very far end of the just reaching the hardware, and with units of functionality, independently of the structure or the architecture that we have, one after another in a slicing mode. The goals of the application test suite is to capture the product specifications. It will allow us to implement them without introducing errors, safely and incrementally, and specify them for different system or product configurations, while reducing or removing the hardware bottleneck related uncertainties and delays. I want to emphasize that these specifications could be functional or not functional. We could do whatever we want here. So what we have done is we have accomplished is to have a plugin architecture, which means that we have drawn a line and we have made that all our business logic, it's at a higher level, everything that wants to work with this business level is going to be a plugin. So we have made all the hardware, including the microcontroller unit, a plugin to the business logic. As a final bonus, I'm just ending. Fallacies and mantras. Debugging is part of development. No, debugging is a shame. While debugging, we are not creating anything. We are adding zero value to organizations. We have to take this into account. Measure your lead time in order to objectively know which are your bottlenecks. You will be surprised. Another of the fallacies is that TDD is a testing technique. No, it isn't. It is a development and design technique. Another of the most common fallacies in the development world is that we can get the same benefits following a test later approach, and that's completely wrong. Test later are testing techniques focused on external quality only. They have nothing to say about the design or the development. Final takeaways. You can't be agile if your code sucks. You can't improve your code if you fear to refactor it. And you can fearless refactor it without a comprehensive suite of tests. So, as a closing advice from the master Dijkstra, we should raise our quality standard as high as we can live with, because it's the only way to discovering how that boundary should be moved forward. And in my case, the only way I have found so far to do that is to follow TDD. Well, this is the end of my talk. I hope that it has been interesting for some of you. I would have liked to do a little code example, but that will require much more time. If there's someone interested in this or in commenting any other matter, you can contact me through my website, Twitter, or LinkedIn. Thank you all.